In this chapter, we will be studying quadratic functions. In this lesson, we will be finding the roots of quadratic equations.
Hi everyone. So now what we're going to do is we're going to take a look at finding the roots of quadratic equations. Okay. Up until this point, we have spent the majority of our time focused on the vertex of the parabola and how to find the vertex. Now we're going to switch gears and we're going to look at a different part of the parabola. We're going to look at the x-intercepts here. Okay. So when you take a quadratic function, you set it equal to 0. What you actually do is you create an equation, okay? So a function is a relationship between two variables, like x and y, okay? Or it can be more than just two variables, but that's typically where we start here, is it's between x and y. As soon as you get rid of the y variable, you throw in a number there, specifically 0 in this case, you create a quadratic equation. And you can solve that. You can figure out specific values of x that make that true, okay? And when you get those solutions, when you get those values, they can be called either roots or solutions here. So there are a few different ways you can talk about basically the same thing. Now, here's a picture of a graph. Here's a picture of negative x squared minus 2x plus 3. We are looking at the x-intercepts of the graph. So here's the parabola. Our focus is now on those particular points here. So we would call those the x-intercepts of that graph, and they are negative 3 and 1. But we can talk about this relationship in a slightly more abstract sense, okay, where we drop the graph and we talk about it really just in terms of your y and your x, a relationship between two variables. In which case, we call the exact same thing the zeros of the function. And what we mean by that is when you take the function here, the f of x, which we know is the representative of the dependent variable, or y, if we make that equal to 0, we're looking for the values of the independent variable, x, that make that statement true. Okay, we call those the zeros of the function. It's the same thing. Okay, remember, because if you're looking for the x-intercepts of the graph, you're going to make the y-coordinate equal to 0. That's where it hits the x-axis. The other way that we can talk about the exact same thing is to refer to it as the roots of the equation x squared minus 2x minus 3 is equal to 0. Now notice that there's no dependent variable here. It's just this equation equal to 0. It's only got the one variable in it. This is something that could be solved. And the answer to that is going to be negative 3 and 1. Now, you replace the 0 here with a y, it becomes a function, graph it, and there's your graph again, and we're looking for the x-intercepts. They all mean basically the same thing. There's just three different ways that you can approach it. That's what I want to get across here as we start this. It's just so that you're not confused by some of the vocabulary. Okay, if we start talking about the x-intercepts, the zeros, or the roots of the function, you know exactly what we're referring to. And there's going to be a few ways that we're going to do this. Okay, we can find these roots because we know that we're talking about the x-intercepts. We can do this graphically. We can do it by factoring. Okay, and you've done that before. In fact, we've practiced that earlier. You can also do this by completing the square. Now, this is an interesting one here because normally this finds the vertex. Okay, but I'm going to show you how you can use that method here. And just once you get it into that vertex form, you can keep going to find the roots. And then lastly, we're going to take a look at the quadratic formula. As it says here, we're going to do this in the next lesson because this is going to require a little bit more attention. But man, once you've got that quadratic formula, you're set. Okay, it's a great little tool. So now what we're going to do here is we're going to kind of approach this one method at a time.
And the first method we're going to use is factoring.
All right, well, the first method we're going to use to find the x-intercepts or the roots of the zeros, we're going to solve by factoring. Now, there are lots of different things you've got to pay attention to when you're factoring. Okay, you've got common factors, difference of squares, you got the grouping or substitution. Okay, there's a bunch of things that you can do here to factor. What I want to talk about really, really quickly, though, is just the concept, what it is that we're actually trying to do here. So I want you to think of it like this. If you've got a times b, and that is equal to 1, the question is, what are the values of a and b? And you might immediately say, well, there got to be 1 and 1. That would be true. But if a is 2, b could be 1/2. Or those could flip. If a is 3, b could be 1/3. Okay? Then you throw in the negative possibilities in here. It just turns out there's an infinite number of possibilities for creating a product of 1. Now, that's true regardless of what number you put here. If you put a 2 here, there's an infinite number of possibilities. That's not enough information for us to zero in okay, to zero in on one particular value that makes this true here. But if the product is 0, oh, okay, well then I know something very, very specific. Okay, I know that at least one of these two must be 0. When I said it was 1, I mean, A or B could have been anything, and then obviously you would respond, like if you pick a number for A could be 10, B would be 1/10. But A could have been anything. But as soon as you throw a 0 here as a product, I already know one of them has to be 0. Either A is equal to 0 or B is equal to 0. One of those two. Now, if A is equal to 0, I don't need B to be equal to 0. That doesn't have to be 0. But if A isn't 0, then B must be 0. It has to be either this or this is true to make this work. And that is the whole idea behind solving by factoring. As soon as I break it down into two expressions multiplied together and their product is equal to 0, one of them must be 0. And then you explore what happens if either one gets set to 0. And at the same time, you don't care about the other one. So when I set A equal to 0, I do not care what happens to B because it doesn't matter what happens to B. If I let B go to 0, I don't care about A. It doesn't matter what happens to A. If B is equal to 0, their product is going to be 0. Okay, so let's kind of, with that thinking in mind, let's solve a few of these and look for their x-intercepts here. Let's take a quick look at this guy right here. Maybe I'll zoom in a little bit. So 5x squared plus 15x minus 20 is equal to 0. Okay, the first thing that I want to do, because I'm really, really lazy, so I'm going to factor out the common 5. Okay, so that'll be 5 and then multiplied by x squared plus 3x minus 4 is equal to 0. Now, I'm going to break this down into two binomial factors here. I know that these first two terms here both have to be x, because when I multiply them together, I'm going to get the first term in my trinomial here, which is x squared. So it's both got to be x. Then I need these last two here to be factors of 4. Now that could be 2 and 2, but when I multiply this out, when I try to get the outer and the inner terms to work out, I don't get them to add together to get 3. Remember, the sum of the outer and the inner terms here should be equal to 3. So that's not going to work as 2 and 2. So it's got to be 4 and 1. Got to be 4 and 1. Now I got to take a look at the sign here. Because it's negative, okay, one of them is negative, one of them is positive, and because the 3 here is positive, because the sum of the two is positive, the larger one's got to be positive, the smaller one's got to be negative. And so that's how I go about factoring. Really what my method amounts to here is guessing and checking, okay? But at this point here, with what we're going to do, and the sorts of quadratic expressions that we're going to be working with here, usually guessing and checking is the fastest method. Now, take a look at this. I've got 3 factors multiplied together giving me 0. Now that means either the 5 is equal to 0, x plus 4 is equal to 0, or x minus 1 is equal to 0. They're not all 0 simultaneously. And this one here makes absolutely no sense. 5 does not equal 0, so that's a done deal. But x plus 4 could equal 0 if x is equal to negative 4. Okay, so there's a possibility. X minus 1 could equal 0 if x was equal to positive 1. And so there's a possibility. And so the two roots of this equation here would be negative 4 and positive 1. Now, graphically, if I was to replace that 0 up there with a y and graph this thing, that would mean my x-intercepts would be at negative 4 and 1. Okay, let's take a look at this next one. Okay, 3x squared plus 14x minus 5. Now again, because I'm lazy, the first thing I want to do is take out any common factors, but I don't see anything that's common there. So I'm going to break this apart into two binomial factors. Now, 3x squared, okay, that first term here. The nice thing about this is that 3 is a prime factor, so it really can only be broken down into 3 and 1. So 3x and 1x. Okay, I like that. Now, 5, again, is another prime factor, which means it can only be broken down into 1 and 5. So it's either going to be 1 and 5 or 5 and 1. Now, I know 5 and 1 won't work because if I multiply out my outer and my inner products here, 3 times 1 is going to be 3, 5 times 1 is 5, and I'm not going to be able to combine those two to get 14. So that's not a very good guess. Okay, so let's switch those around. Let's put the 1 here and the 5 here. 3 times 5 is 15, and 1 Yeah, I can make that equal to 14 so long as this is positive and this is negative. And actually that works out totally fine because negative 1 times 5 is negative 5, and that's what I wanted down there. So now I've got it broken down into two factors. Because their product is equal to 0, either 3x minus 1 is equal to 0 or x plus 5 is equal to 0. One of those two would make this whole product go to 0. Bring the 1 over, so 3x is equal to 1. Then divide both sides of that little equation there by 3, and I'll get x is equal to 1/3. If x is 1/3, that whole expression goes to 0. Or it could be the case that x plus 5 is equal to 0, in which case bring the 5 over and I get negative 5. So my other root here is going to be negative 5. Either one of those will make that expression equal to 0. So those are the zeros of the function. Now, finally, in this case right here, and this is again just to review the concept here, notice that this has already been factored for us. It is equal to 0. If this wasn't equal to 0, okay, I would have to make it equal to 0. If it wasn't equal to 0, then I'm stuck. So what I would end up doing is expanding this whole thing over, bringing whatever number was here, bringing it over, and then trying to factor it again. But in this case, they did it for us here. So now remember how I approached that here. I've got three different factors multiplied together. So either 3 is equal to 0, 2x minus 5 is equal to 0, or x plus 1 is equal to 0. Now 3 doesn't equal 0, so that's not the thing right there. That's not giving me any useful information. But 2x minus 5 could equal 0. Bring the 5 over. 2x minus 5 will equal to 0 if x is equal to, and let's divide by 2 here, if x is equal to 5 halves. Okay? So 5 halves makes this expression goes to 0, which makes the product go to 0. That would be a solution. Or x plus 1 is equal to 0, which means x is going to equal negative 1. Negative 1 makes this factor here equal to 0, and that means the whole product there is equal to 0. That's a solution. So my two roots there are 5 halves and negative 1. Now, don't overthink this thing too much and get caught up in this. 5 halves doesn't make x plus 1 equal to 0. Okay? It doesn't. If you plug 5 halves into this, you get, what is it? You're going to get 7 halves. But that's not the point. It makes this expression here equal to 0, and when you multiply that all together, the total product is equal to 0, and that's what's important here with each of those. Okay, now we're going to move on and we're going to solve the next few equations here, doing two different methods here. And I really got to compliment the writers of our book here, Mrs. McIntyre and Mrs. Isidoro here. This is a wonderful little transition to where we're going. So, first of all, x squared minus 25 is equal to 0. We're going to solve this by factoring. Now notice this is a difference of squares. So this factors down into x minus 5, x plus 5 is equal to 0. I take the individual factors and set them equal to 0 because I don't know which one it is. Could be both. And so this means either x is equal to positive 5 or x is equal to negative 5. Both of those would be solutions. But the other way that we could have solved this was by isolating the square. Now we started with x squared minus 25 is equal to 0. And what I can do is I can bring that 25 over to the other side of the equation to get x squared is equal to 25. Now my next step is to take the square root of both sides, but bearing in mind that this is an algebraic expression here and I'm squaring the x, what this is saying here is that when I square a number, the result is 25. So bearing in mind, that could be plus or minus 5, okay, the positive or the negative value there. And I need to include both in this particular case. But you see how that gives us the exact same results. Okay, so let's try another one here. X plus 3 squared minus 25 is equal to 0. Now, notice that I've got this x plus 3 in here. Now, I'm going to solve this by factoring first. But I've got this x plus 3 in there, and that's kind of confusing. So I'm going to let a be x plus 3, because I don't know what x is, which means at the same time, I don't know what x plus 3 is. That's x plus 3 is as much a variable as x. So I'm going to write this as a squared minus 25. Now, we just saw that that would mean that a minus 5, sorry, that the factoring here is a minus 5 or a plus 5 is equal to 0. So once I've got it down to here, what I would do is I would replace that a with x plus 3. So this would be x plus 3 minus 5, x plus 3 plus 5 is equal to 0. And then I would simplify that. Now I know someone's saying I could have probably done this in a slightly different way, like gone down to the a equals plus or minus 5. But this is how we had done the factoring before, and I need to remind you of that so you've seen it again. So this becomes x plus 3 minus 5 is going to be x minus 2. X plus 3 plus 5 is x plus 8 is equal to 0, which means either x minus 2 is equal to 0 or x plus 8 is equal to 0, one of those two, in which case x is either equal to positive 2 or x is equal to negative 8. Those are my two solutions. Now, the other way that we could handle a problem like this, and I'm going to rewrite the question here. The original question said x plus 3 squared minus 25 is equal to 0. The first thing I could do is isolate the square. So make that x plus 3 squared is equal to 25. Now just like we did above, I'm going to take the square root of both sides, but again, this in this form, the way it's written, this algebraic expression is being squared. And whenever I square something, I don't know whether the original was positive or negative just looking at the result here. So this could be positive or negative 5 when I do that. And now what I'll do is I'll bring that 3 over and subtract it. So my result is going to be negative 3 plus or minus 5. Okay, I subtract the 3 from both sides, but I don't know whether this is supposed to be positive 5 or negative 5. Now let's put those together. And what I'm going to get here is negative 3 plus 5. Okay, is going to give me positive 2. Negative 3 minus 5 would give me negative 8. There are two different possibilities here, and I need to write down both. Now, please notice the way I've written this. Notation is so important in mathematics. Okay, I did not put parentheses around that. As soon as you put parentheses around that, that makes this the x coordinate, that makes this the y coordinate. Okay, please don't think in your head that putting parentheses here is just your little way of grouping the answers together. That's incorrect. Okay, that's not the way you want to handle that. X is either equal to 2 or it's equal to negative 8. I just list them using the comma there. So just be careful. Let's do this one more time here. Okay, 3 times x minus 2 squared minus 27 is equal to 0. Now, the first thing that I see here is there's a common 3. Like when I'm looking at this, I'm looking for a difference of squares. I see a square, but the 27 is not a square number here. But I can factor out a 3. That'll make this x minus 2 squared minus 9 is equal to 0. Now I run into a similar sort of situation that I had above. I'm going to let a be x minus 2. And so this becomes 3 times a squared minus 9 is equal to 0, which I can factor down to 3 times a minus 3, a plus 3, because now that's a very kind of clean difference of squares there. Now I'm going to plug back in that a was equal to x minus 2. So this is going to become 3 times x minus 2, whoops, look at this right here. There's my a, x minus 2 is the a, minus 3. Okay, that was that additional minus 3. Then I move over, there's my a is x minus 2, so x minus 2 plus 3. And that was equal to 0. And again, I'm doing it like this, okay, because of an ulterior motive. I want to make sure that we're consistent with how we factored in the past. This will become x minus 2 minus 3 is x minus 5. X minus 2 plus 3 is going to be x plus 1, all equal to 0. And so now either 3 is equal to 0, and I hope you're seeing the pattern here. That doesn't make any sense. 3 isn't 0. Or x minus 5 could be equal to 0, or x plus 1 could be equal to 0, in which case my solutions could be 5 or negative 1. Okay, those are my two roots. Now, I could get the exact same result here by initially isolating the squares. So let's do the same thing here. So we've got 3 times x minus 2 squared minus 27 is equal to 0. Now, first thing I would do is bring over that 27. Okay. Now, I want to work my way in to the x in this expression here. So bit by bit, I'm going to chip away at this expression until I get to inside here. So first of all, I've got this 3 on this outside. I'm going to divide both sides by 3. So x minus 2 squared is going to equal 9. The next thing I got to chip away at here is this square. I'm going to take the square root of both sides, again bearing in mind that because I was squaring this value, I don't know whether the original was supposed to be or was intended to be positive or negative 3. Now I'm going to add the 2 to both sides, so 2, I still don't know which one that was supposed to be. It could have been positive or negative 3, but now I'm going to explore what happens with each one. 2 plus 3 is 5. 2 minus 3 would be -1. And so there again, we get the same results that we got earlier here. Okay, and bear in mind, again, I'm not putting parentheses around that to group together those answers. That all of a sudden changes that expression into something very different and not what I want to answer there. Okay, I hope that makes sense. This is a nice little transition to where we're going next.
Now we'll look at solving quadratic equations by completing the square.
Okay, for this next set of questions here, what we're going to do here is we're going to solve by completing the square first, and we're going to do this graphically. I'll show you how to do that graphically. But we're going to solve by completing the square first. Now, I hope you noticed in that previous question that when we were looking at these expressions here, the expressions on the left-hand side here, that's in vertex form. That's in vertex form. This one's a little less obvious, but that one right there, again, x squared minus 25, that is in vertex form. Okay? So what we've just established, and this is one of those wonderful traits of mathematicians, I just love this. Okay, in a math context, often you can take your questions and say, hey, I don't know how to solve that, but I'm going to take that question and I'm going to make that look like something I can solve. So I'm going to change the question. In this case, what we're going to do is we're going to change it by completing the square. Okay, now, if you think about how we have done this in the past year, the very first thing I'm going to do is I'm going to move that -15 way over here. Okay, and I'm going to leave my quadratic and my linear term kind of isolated over here. This is where the work is going to occur. I don't care about the -15 for the time being. Normally I would take out the leading coefficient, but it's 1, so I'm okay. So now I take a look at this middle term, and I already know, because that's -6, I already know that 2 steps down, I am going to get x minus, and I take half of that number, -3 squared. Okay, I already know this is going to be what's inside my parentheses when I have this in vertex form, because it's always 1/2 of the coefficient of the linear term. Now, what I got to do is I got to figure out what's going on outside here, though, and the way I do that is I take that -3 and I'm going to square it, and I'm going to add it here and subtract it here. So -3 squared is going to be +9. I add that first of all. Now bear in mind, the reason why I'm doing it like this is x squared minus 6x plus 9 always factors down to this x minus 3 squared. That will always factor down. That's why I did it. Oftentimes I'll get people ask, where did the 6 go, or where did the 9 go? Well, okay, look, it's right here. X minus 3 squared, if you expand that out, you get that. But I can't just randomly add a 9, so I'm going to subtract the 9. In this next step here, what I do, and this is, in this particular case here, this is kind of a trivial little thing to do here, but often if there's a coefficient, this step isn't trivial. I'm going to group together these constants out back here. Now, -9 minus 15 is going to be -24. Okay? Now, this is in vertex form. Now what I can do is bring over the 24. Okay, add that to both sides. I'm now going to take the square root of both sides. I know this is going to be plus or minus the square root of 24. The thing is, I just don't know what the square root of 24 is. Now I'm going to simplify that in a second. First of all, I'm going to bring the 3 over, add the 3, plus or minus, okay, 24. 24, if you write that down in terms of prime factors, would be 2 times 2 times 2 times 3. Okay, 2 times 2 times 2 times 3. So there's a pair of 2's there that I can pull out. So this will be 2 root, and there's a 6 left over. This is in exact form. Okay, that is the exact form of my answer. As soon as I go to my calculator and identify what the root 6 is, as soon as I do that, I'm going to have to round my answer. Now, I am going to do this because I'm going to use the calculator to do a graphical solution here in just a second. So, but here's my answer here. 3 plus 2 root 6. I'm going to get 7.9. Okay? So this is going to equal 7.9, or, do that again, but this time we'll change that into a subtraction. Press enter, and I'm going to get negative 1.9. So those are the two solutions that I get in decimal form. Those are not exact answers, those are rounded. Okay, as soon as I went to the calculator, I had to round that. Now, let's take a look at what the graphical solution would look like. What I'm going to do is I'm going to go to my y equals, and I'm going to enter my equation. Instead of putting the 0 in there, though, I'm going to replace the 0 with y. So this will become x squared minus 6x minus 15. Right now, I don't really know what my window settings should be. Now, the graph is right there, but just let's pretend here. So I'm just going to press graph and see what I see. Okay, so there's my parabola coming down, going up here. It probably helped me out here if I could see what's going on down here. So let's press my window. I need to make my Y min a little bit more min. Okay, let's try negative 20. Does that do it? I'm just guessing here, I don't know. Actually, I mean, I do have a really good hint here, but just to show you here that how you might approach this, okay? I mean, there are other kind of clues as to what's going on here. We'll talk about that in just a second. Let's maybe make that negative 30. Why not? Let's see if that works. There we go. There's the bottom here. Now, I actually knew what that minimum had to be, because bear in mind, when I completed the square, I put this into vertex form. I knew that the y-coordinate of the vertex was negative 24. So I could have actually adjusted my guess based on that. But oftentimes I'll see students that are stuck because they're not comfortable just guessing and just adjusting that. There's nothing wrong with just guessing and trying to expand out the window bit by bit there. So let's find the x-intercepts here. So we press second, trace. The calculator calls these things zeros. We're looking for the zero of the function here. And the way you do that, the x-intercept I'm looking for is roughly right there. Okay, I'm using the left and right arrow keys on my calculator, and I'm going to move my cursor to the left and press enter. Okay, there's going to be a left bound right there. Then I'm going to move my cursor to the right, press enter. So as long as that x-intercept is in between the two lines here, I should be good. Press enter, and I get negative 1.9. Sorry, and then you saw that. Okay, I already wrote that down here. So let's do this one more time. So second trace, 0, and we're just going to quickly go over to the other side here. It's the exact same thing. You just got to do it. Just got to do it twice here. I'm to the left. I press enter. I move to the right. I press enter. As long as the x-intercept is in between those two, when I press enter, and I get 7.9 as my root. So it works. Okay. Was able to use the calculator to find those particular x-intercepts as well. All right, let's take a look at this next question. When I see it written like this, the first thing I see is this fraction here. Because it's an equation, I'm going to get rid of that fraction. I'm just going to multiply everything through by 2, and that's going to get me x squared minus 6x plus 10 is equal to 0. Okay, and I find that a lot easier to work with right now. And I haven't really done anything because it's an equation here. So now, just like I did before, I'm going to move that 10 out of the way, that positive 10, and I'm going to leave this x squared minus 6x over here. Now, in exactly the same way, okay, I'm going to complete this square or up top here. I know that 2 steps down, this is going to end up being x minus 3 squared. In fact, it's the exact same thing as we just did previously here. Then I'm going to take that negative 3, square it to get positive 9 minus 9. X squared minus 6x plus 9. And I'm going to group together the negative 9 and the positive 10 here. And so that's going to get me positive 1 is equal to 0. Okay? Now I've got this thing in vertex form. Now I'm going to try to solve for the x-intercepts here. I'm going to bring over that 1, x minus 3 squared, whoops, is equal to negative 1. And now I'm going to run into problems here because when I try to solve that, okay, when I try to now go to the next step by taking the square root, I'm going to end up taking the square root of a negative, and that's not going to get me any real solutions. I'm going to get no real solutions here. I would have to start using imaginary numbers to make that work, and we're just not prepared to go there in this particular course here. So what's going on here? What happens? Well, let's take a look back up here at what that parabola would look like. Okay, if you take and put this on the grid here, notice that your vertex is going to be the point 3, 1. So let's go over here. 3, 1, right there. I know that this thing opens upward because the leading coefficient here is positive. In fact, we're going to go one step further here. Let's figure out what the y-intercept would be. If I made x equal to 0, 0 minus 3 is going to be negative 3, squared is going to be 9, plus 1 is 10. So this thing's going to have a y-intercept up here as 10. This is 1, 2, 3, 4, 5, 6. Okay, it's way up here. So this thing's actually going to open up something like this. So no wonder we run into a situation here where there is no solution. Okay, I just want you to be aware that that sort of a situation can happen here where you end up with no real solutions, and that's because the parabola doesn't intersect with the x-axis at all. And that's totally fine. Don't get nervous when you get into a situation like this, let's say on an exam, and you get this square root of the negative here, no real solutions, what do? I've watched students who kind of out of that sense of nervousness there and anxiety will make that positive because they think they made a mistake somewhere and they're trying to correct it. And then it just gets worse from there. Okay? This is not a problem at all. Just have faith. All right, now we're going to solve some word problems related to what we've just been working on. Now notice what, the question that I'm working on here, and you're going to see something very familiar about it, but there is something significantly different about the way this question's worded that requires a different approach than what we've been applying earlier. So now notice the length of a field is 20 meters less than twice the width. Okay, let's draw that out there. Okay, so here's the width, here's the length. What is it telling us here? The length of the field is 20 meters less than. Okay, so this is going to be minus 20. I'm going to be subtracting 20 from something. Twice the width. Okay, twice the width. Now, thus far, this looks very similar to some of the questions that we did before, where we were looking for the maximum area of the field here, given certain constraints here. But the difference here is, look at the rest of the question. It says, if the area of the field is 6,000. It's like, oh, they told us what the area is. Oh, okay. So the area of the field, which would be length times width, is 6,000. So then the question is, find the dimensions. Okay, so what we're going to do here is we're going to take this 2w minus 20, just like we did previously when we worked with problems that looked similar to this. We're going to do a little substitution here. It's just that we're missing a variable. In the previous kind of iterations of this problem, there was that third variable that we were trying to maximize, so we would do a substitution and then complete the square. Now if you do the substitution, we're going to get 2w minus 20 multiplied by w is equal to 6,000. When I expand that out, I'm going to get 2w squared minus 20w equals 6,000. Notice that I don't have that other variable. Okay? I'm not going to be completing the square here. In fact, I'm going to bring that 6,000 over because now all I've got is one variable. I need to solve for that variable. Okay? So I get this equal to 0. I'm going to try to factor this or complete the square to solve it. Now I am going to try to factor this to start off with. I'll take out the common 2, see what I get. Minus 10w, and that's going to be minus 3,000. It's equal to 0. Okay, so now factors of 3,000 that differ by 10 here. Let's just take a quick look here. Now I'm going to show you a little trick here, something that you might want to do here. I am looking for factors of negative 3,000 that differ by 10. So what I'm going to do is I'm going to go y equals, whoops, that's an old one there. I'm going to type in negative 3,000 divided by x. Okay, this is just a little way that you could use your calculator to help you out here. Then instead of graphing this, I'm going to go second table to get to my table of values here. I'll come down, okay. So what I do is I come down to 0, and now I'm just going to start to run through here. I'm going to go down, and I'm going to look for where these factors, because this is telling me that 9 is a factor. Okay, here, 10 is a factor, so is negative 300. I'm going to keep going until I get those two adding up to 10, negative 10 here. So I got 20 and negative 150, 24 and negative 125, nope. 30 and 100, nope. We're looking for that pair that differ by 10. Now we're getting close. 40 and negative 75. Ooh. And there it is right there. 50 and negative 60. Okay, 50 and negative 60 will add up to negative 10. So now, if I never once found a set of factors that did that, like if they kind of passed each other and then all of a sudden the numbers started to repeat on one side. So if I started seeing like if I got up to 60 here, for example, if I get up to 60 here on in the black numbers, the x values here, I've gone beyond. So these guys have passed each other, and that's not going to work here. But I know that my factors here are now going to be 2 times, this will be w minus 60, w plus 50 is equal to 0. And now either that factor, w minus 60 is equal to 0, or w plus 50 is equal to 0. So the width here could be 60, or the width here could be negative 50. Now negative 50 doesn't make any sense, so the answer that I'm looking for here would be 60. And if that's true, then we know that L, so therefore L is going to be 2 times 60 minus 20. Okay, let's just think about that. 2 times 60 is going to be 120 minus 20 is going to be 100. So my width is going to be 60 meters. My length, okay, is going to be 100 meters. Now, when you multiply those together, do you get 6,000? Oh, you can't quite see it. Do I get 6,000? Yes, I do. So those are the length and the width that we were looking for. In this question, we have a similar sort of scenario to what happened before. The previous question, again, it has the look to something that's going to be like a max or min problem, but then they give you an extra bit of information that kind of changes that. So what we read here is an open top box is made from a 14 centimeter by 20 centimeter piece of flat cardboard. Okay, then 4 congruent squares are cut from each corner. Now congruent simply means that they're all the same size, same shape. Okay, and then you fold it up here. So you cut out the corners, and then we're going to fold along these dotted lines here, and that's what's going to make this box here. Okay, now we're told that the finished box has a base area of 216 inches squared. Now I'm assuming that the change in units here is a mistake. It said 20 centimeters and then all of a sudden changed to inches here. So let's just assume that that's a misprint here, that what it meant to say was 216 square centimeters. Okay, and here we go. How are we going about doing that? Well, first of all, bear in mind that here's the base. Okay, that you're going to fold up this piece. You're going to fold up this piece. So this is going to be the bottom of the box here. Now, this distance from here to here was 20. I cut an X out of this side. I cut an X out of this side. So that's 2 X lengths cut out of that. So this distance right here is 20 minus 2X. We can make a similar argument along the width here. This distance from here to here was 14, but we cut out this X and then this X length here, and then we're folding it up. So we're going to lose this, and we're going to lose this up here. So this distance right here is going to be 14 minus 2X. Okay? And so now we know the base area is going to be, now first of all, we know it's going to be 216. We know that. And that's going to be length times width. And in this case, that's going to be 20 minus 2x, okay, multiplied by 14 minus 2x. Okay, and so when we multiply those together and expand that out, we're going to get here's the 216. We'll leave that for now. I got to expand this out here because remember, in order to solve an equation like this, and I am solving it because there's only one variable in here. Okay, in order for me to do that, I need to expand this out. I need to bring the 216 over because I need it to be equal to 0. Okay, and then I need to factor it. So this is already in factored form, but it's not equal to 0. So I got to expand it first. So that will be, what is that? It'll be 280 minus 40x minus 28x. This will be plus 4x squared. Okay, now we'll bring that stuff over there. Okay, we'll bring the 216 over. I'm going to reorganize this as well. Make that 4x squared. What is that going to be? Minus 68x. And then this will be plus 64 when we bring the 216 over. Okay, now when I look at this, I kind of want to divide everything through by 4. And that's going to give me x squared minus 17x plus 16. Okay, now I was a little nervous about how that was going to solve here, but actually this is going to be okay. This will be x minus 16, x minus 1. And so my two values here are going to be positive 16 and 1. Okay, there we go. Until I think a little bit more about what this scenario is here. 16. Okay, remember that x is the size, okay, size of the square that we're cutting out. So let's just go back and take a look at it. X is supposed to be the size of the square that we're cutting out. So I just found that X could be either 16 or 1. Now wait a minute, 16. 16 doesn't make any sense. Here's 20. It's 20 centimeters across. 16 would put me over here. Okay? So cutting out this gigantic square, and then from this corner cutting it out over here. Like, I've got these huge overlapping squares that cut out the whole thing. Like, there's not possible. I cannot cut 16 by 16 squares out of the corners of this cardboard box here. That doesn't make any sense at all. Okay? So it can't be 16. It's got to be 1. 1 makes sense. I can do that. I can lose 1 from all the corners here. And in fact, when we do that, you think about your length, width, and height here. The length of our box, okay, it was 20 centimeters, but I'm going to lose 1 on either end here. So 20, lose 1 is going to be 18 centimeters. The width here was 14, but I'm losing 1. So 14 minus 1 is going to be 12 centimeters. And then the height, well, now just think about it. When I cut these corners out here, this was 1 by 1. Then I took this rectangle here, which is going to be 1 by, now in this case we just discovered this is going to be 12. I'm going to fold that up, and so that width there, is that X is going to end up being my height. So my height is going to be 1 centimeter in this particular case. And those are the dimensions of the box. But you got to be clever. Don't just take the answer that you get here and run with it. You got to make sure that answer actually makes sense in the context of the question. All right, now the last question we're going to do looks like it says a gardener surrounds a 4 by 8 meter flower bed. So here we go, 4 meters by 8 meters, with a border of wood chips, and then the area of the wood chips is 28 meters squared. We're supposed to figure out how wide the border is. So that's going to be a constant all the way around. Let's just call that X. Okay, so that width right there is going to end up being X. Now you can't, I can't hardly see that here, but let's just do it like this. So that width right there is going to be X, and then so will that as you go all the way around here. Now, let's just think about the scenario here. The area that I've got. Now, probably the easiest way to do it would be to figure out what the area is of the whole thing, and then subtract the area of what's inside here. Now, and we know, if this is 4 by 8, that the area here is going to be 32 meters squared. What I need is that outer area, okay, and I know that it's going to be 28. Okay, I know that the difference between the areas is going to be 28, and that is going to be 8 plus x plus x, so that the width of the larger square is going to be 8 plus x, so 8 plus 2x. The width, okay, well, the width of this guy right here is 4, and then it's going to go x and x out this way, so this is also going to be 4 plus 2x. Okay, so, and then from here I'm going to subtract the 32, whoops, you can't see that, the 32 meters cubed, sorry, square, cubed, no, not cubed, 32 meters squared that you get for that middle flower bed. So this is the outer, the whole rectangle, including the flower bed and the border. This is just the flower bed, and the difference is supposed to be 28. Okay, so here we go. I got to expand this all out because I need this to be equal to 0. So I'm going to bring that over. Okay, so we're going to end up with, now way at the back here, we're going to get negative 32, then we're going to subtract that 28 first. So back here is going to be negative 60. Now I'm going to expand this out. It'll be 32, and that'll be 16. When I multiply those out, 16 plus 8, so 24x plus 4x squared. So what do I get here? Putting that together, I'm going to get 4x squared plus 24x, and then I've got 32 minus that 60 there. Oops, 32 minus 60. Just want to double check on my calculator because I don't want to do that wrong. Okay, good. Now I'm going to divide out a 4 out of all that. I'll get x plus 6x, whoops, x squared I should say, plus 6x minus 7. And I love that because 7 is a prime factor. It only gives me the two options here. And I can put those two prime factors together to get the 6 there. So x plus 7, x minus 1. And notice when I multiply the 7 and the negative 1, I get the negative 7 here. So x plus 7 could be 0, x minus 1 could be 0. Now the 4 isn't. That factor isn't making this thing equal to 0, but this factor could, and so could this one. Which which means x could either be -7 or x could be 1. Now, in the context of this question, I hope it's obvious that doesn't make any sense. It doesn't make any sense for the width of this border to be -7 meters. Okay, that's just a product of kind of the algebraic features of this little equation that we just solved. This one makes way more sense. Okay, so the border is 1 meter wide. That's the answer we're looking for.